Okay, let's try to finish this Gaussian channel here. This chapter is a bit long. Okay, so the Gaussian channel model in its simplest form consists of input and output alphabet that are real numbers, and is simply represented by this input-output relation, where y is optionally a scaling g times x plus z. Z is Gaussian noise. We use this symbol n0 half. In communication theory, n0 half is used as the noise power spectral density for continuous time channel models. This is discrete time, so these relations represent the one channel use. It means that at every time I, we receive real number yi equal to g times xi plus zi, and this sequence zi is iid with this distribution. There is a sequence of Gaussian random variables, independent and identically distributed. In order to make the problem meaningful, we need to have an input constraint, so a input cost constraint, because otherwise you understand that if we have all the real numbers to communicate with, we can basically choose points on the real line infinitely far apart, and we can communicate whatever data essentially error-free. But this doesn't make sense because from a physical viewpoint, imagine that the xi's are samples from a signal. So we cannot arbitrarily pick those samples. There are some constraints, and in particular, a typical constraint is this called power constraint, or better, energy per symbol constraint. So the square of a signal sample is related to the energy of the signal. So summing all the samples together for the whole block length n and divided by n gives us a limitation in the energy per symbol, and we require that every code word, in order to be admissible for every m are the information messages, every code word must satisfy this energy per symbol constraint. So this means that imagine that if we represent the code words in an n-dimensional real space, well, a code word, a code word x m, so the mth code word is simply an m-dimensional vector, and the constraint is that the length of this vector, so when I sum the squares of the components, okay, this is simply what we refer to as the L2 norm square of the vector, which is its length. If actually its length square, if I take the square root of this is precisely the length of the vector. Okay, so this means that in an n-dimensional space there is a sphere of radius square root n es, and the code words are points on the surface of this sphere, or in fact the points inside the spheres. They cannot be outside because otherwise the constraint, the average energy per symbol constraint, is violated. So this is the geometric picture of code books for the Gaussian channel. This is an n-dimensional sphere. Okay, good. So for this channel, we have the theorem that says the capacity of the AWGN channel, AWGN means additive wide Gaussian noise channel, with received signal-to-noise ratio SNR. Signal-to-noise ratio is signal power divided by noise power, and here is given by, at the receiver, SNR is, well, we receive energy per symbol G squared times ES divided by the noise variance per component N0 half. So we have 2G squared ES divided by N0. The capacity is given by this formula. And the capacity is measured in bits per sample, or bit per symbol, or also bit per channel use, where one use of the channel consists of sending one sample through the channel. So, well, this is a very famous formula in information theory. Some people call it Shannon's formula. Well, you know, there are many Shannon's formulas. Shannon wrote a lot of formulas. I don't know why this is referred to that, but okay. Now we are going to prove this theorem, and then we're going to elaborate and relate this formula to more, say, quantities with a more clear physical meaning for this channel. So without loss of generality, you understand that we can prove everything for G equal to 1, so unit gain, and then simply rescale the signal-to-noise ratio according to the gain of the channel, so the attenuation that the signals is going through the channel. That's not a problem. And this simplifies a little bit the notation. So we want to prove this formula. So let's first show that this formula is actually obtains the max, in fact, the supremum over all input distribution with fixed second moment, so with a constraint expectation of x squared less or equal than ES of the mutual information. Notice that we already have a capacity theorem. We do not have to reprove it, because in fact we have the general capacity theorem that says this maximum or the supremum is the capacity. So we have just to prove that the solution of this optimization problem is given by that result. So we can write, well, by definition, we simply write the mutual information as the difference between these two entropies, the differential entropies. Then we use the fact that the channel is additive, so y is x plus z here, and this is the differential entropy of x plus z given x, and we know that differential entropy is invariant by translation. When we condition with respect to x, then x acts like a constant, so it can be removed. Once we remove x from here, so basically this is like saying h of x plus z given x is the same as h of z given x, but z is independent from x, and therefore this is simply h of z. And this is generally true for every additive noise channel, that the second term is always the entropy or differential entropy of the noise. We have already seen this for when we treated the binary symmetric channel, if you remember. And so we end up with our maximization, where in fact we just have to maximize this differential entropy, because this part depends only on the noise statistics. So there is nothing to do. In fact, this part is fixed. This is just the differential entropy of the noise. So our maximization problem reduces to find the distribution of x with constraint second moment such that the h of x plus z is maximum. And now we know that if h of x plus z, well, x plus z, since x and z are independent, then the variance of x plus z is the sum of the variances. It must be variance of x, which is at most es by the constraint, plus variance of z, which is n0 half, right? So we are in the case where we have the differential entropy of a variable whose variance is constrained, and then what is the best thing to do is when x plus z is Gaussian. But how do we make x plus z Gaussian when z is Gaussian? There is only one choice, because the sum of two independent Gaussian is Gaussian and there is no other choice. So the only choice to do here is to let x also Gaussian. So by letting x Gaussian with zero mean and variance es, we obtain this maximum. And because the supremum here is obtained with equality by letting x Gaussian. So the optimal input distribution for the Gaussian channel is also Gaussian. The best way to generate random codes, in this case, the intuition is to pick a Gaussian distribution and generate at random Gaussian random vectors, create a family of m of those, 2 to the n r. This will be, with high probability, when n is large, it will be a very good code for the Gaussian additive noise channel. We can also amuse ourselves in a direct proof of the converse. A direct proof because, okay, we can use what we already know, this supremum, well, we have already just calculated the supremum is this, so we are done, right? But if we want to, as an exercise, we can have a direct converse based on finite equality, and again, the property of entropy maximization of the Gaussian random variable. So suppose that we are given a family of codes of block length n, rate r, and vanishing probability of error when n goes to infinity. And suppose that this family of codes satisfy a relaxed input constraint where we take the average of the energy per symbol over all possible code words. So, of course, this is relaxed because we are, instead of imposing this constraint per code word for each m, we impose the constraint only on average over all the code words. So certainly we cannot make worse, so there is no restriction here. In fact, we are enlarging a little bit the family of admissible codes. And then let's see what happens. Using Fano inequality and data processing, we can write n times r is the log of the size of the matched set, so messages are uniform, so it's the entropy of n. Now, Fano inequality, by adding here, basically adding this and subtracting this, we end up with the mutual information between the message and the output plus this conditional entropy, but this conditional entropy can be upper bounded by n times epsilon n by Fano inequality. And then, since there is a Markov chain message, input, output, the mutual information between input and output is always greater or equal to the mutual information between the message and the output, so we end up with this. And this is a very standard way to start with the converse, Then we use again the additivity of the noise, and we break this mutual information in the difference of differential entropy of the output minus differential entropy of the noise. This is the vector of noise, is n-dimensional, so then we write it in this way, right? So now we can say, okay, we have this code. We don't know anything about this code. We cannot assume anything, but for sure, well, there is a marginal distribution for the ith symbol of the induced by choosing the code words with uniform probability and then marginalizing this with respect to the ith letter. So there is, we can compute the variance per component, which will be whatever it is, right? And then we can upper bound this differential entropy using the independence bound. We bound with the sum of the individual differential entropies, and each differential entropy is maximized when the variable yi, which is xi plus zi, is Gaussian. So we have here Gaussian differential entropy per component. We still do not know what these variances are because we cannot assume any distribution on those marginals. They are not Gaussian, nothing. It's just induced by the use of the codebook with uniform probability over the messages. But now we can use the fact that the logarithm is a concave function, and therefore exchanging, so dividing by n and multiplying by n here, this is like expectation over all the symbols. We bring the expectation inside, and we use Jensen's inequality, so we get an upper bound. And now this quantity is precisely what is supposed to be less or equal than ES by this constraint, okay? Because it's the sum of the variances per component, right? So at this point, let me erase some scratches. We use the monotonicity of the logarithm. So this quantity is less or equal than ES, and therefore the whole thing here is less or equal than n divided by 2 logarithm of 2 pi e times n0 plus ES, and then we put everything together here, and what we find is that this is n times then 1/2 log of 1 plus 2es over n0, which is SNR, and then plus n epsilon n. Then all we have to do is to divide by n on both sides, and we end up with if such family of codes exist, the rate must be less than this quantity plus a vanishing quantity here, which proves that this quantity is an upper bound to the capacity. But of course, we have already proved that this quantity is achievable because it's the maximum of the mutual information, and therefore we are done. Okay? So the geometric interpretation here is very nice because when we deal with Gaussian channels, everything becomes really nice and geometric. And also here you get the intuition of why this famous lemma that is at the basis of the proof of the achievability of the channel coding theorem is called sphere packing, because here we are actually packing real spheres in the real space. So as I already said, we are considering geometrically by looking at the n-dimensional real space. Code words are points inside a sphere of radius square root of n times ES. And by the way, the volume of a sphere of radius r in Rn is given by Vn times r to the n, where Vn is the volume of the unit sphere in n dimension. You can also find somewhere, look at Wikipedia, the explicit expression of this. I used to know it by heart, but in this context is irrelevant because it's going to simplify. So you can look at it. Is a known formula. Okay. So basically, what I said is let's look now at the received vector, so the y. Y is x plus z, and z, with very large probability, z is a vector which is contained in a sphere of radius square root of n times n0 half. Why is that? Because by the law of large numbers, if I take 1 over n sum over I of zi square, well, this converges to the variance of the variable z, which is n0 half. So again, we see that this quantity hardens, which means that when n is very large, the noise vectors are contained into these typical noise spheres. So overall, since x and z are independent, these vectors add incoherently, and overall the y is contained in a sphere which is with radius a square root of n times the sum of the two variances. So this is by the law of large numbers. So now what we have this volume, this sphere that contains the output, and now we can pack typical noise spheres inside, right, such that they do not overlap. Why they shouldn't overlap? Well, because if we do this packing, right, imagine that we are transmitting code words which are the center of these typical noise spheres, and these typical noise spheres do not overlap. What happens? The noise is going to add to the transmitted code word. So for example, a typical noise vector will be something that carries this point to inside its sphere, or this point inside its sphere, this point inside its sphere. It will not go out of these typical noise spheres, because otherwise this will be an atypical noise realization. You have like a sort of atypical noise which is stronger than typical, and we know that the probability for this to happen goes to 0 when n goes to infinity. So if these spheres do not overlap, we can precisely recover what was transmitted. If I receive a point, for example, suppose the blue point is the receive point, I receive a point here, well, then I know that this code word was transmitted. If I receive a point, let's say here, oopsie, here, then I know that this code word was transmitted. And the probability of making an error is when the noise is atypical and carries out outside the typical sphere, but this probability becomes very small when n is large. So the problem is how many code words I can use such that these spheres, these typical noise spheres, do not overlap. And the best case is take the volume of the sphere that contains with high probability a typical output, divide by the volume of a typical noise sphere, and this is, let's say, an upper bound, an optimistic upper bound on the number of non-overlapping spheres. Of course, this would be true if there was no space in between. And so that's why it's optimistic. But it turns out that this result becomes exact in the limit for large n. So we do this. Now you see that the Vn and Vn simplify. There are terms that simplify. So we get this number. And this is the number of possible code words. Now we take 1 over n log of this number, and this will be the number of bit per symbol we can transmit. And what we get is 1/2 logarithm of 1 plus SNR. Voila. So by this sphere packing argument, we recover exactly the same formula. Of course, this is not a proof. This is a geometric intuition. But you see that the geometric intuition exactly explains you why we can transmit information through a channel that adds noise and still perfectly recover the message with vanishing probability of error. Because we choose the code words, so the center of the spheres, such that the noise to carry the received signal away from a typical sphere and inside somebody else's sphere, and so make a mistake, is atypical. And so the probability for this to happen becomes very small when n becomes very large. Good. So this is basically the so-called discrete time continuous alphabet additive Gaussian noise channel. Discrete time because I said before the input, the channel used here corresponds to sending a signal sample, so a real number, and receiving a real number. Now we can relate this discrete time channel to what is called a continuous time band limited channel. So in reality, we know that in most communication systems, well, we have a certain channel bandwidth. For example, the bandwidth may be located around the zero frequency, and then we call it a baseband channel. Or the bandwidth may be located around a carrier, a modulated carrier. For example, here, when we have some F0, say, I don't know, in Wi-Fi F0 is 2.4 gigahertz, or in 5G is going to be 3.7 gigahertz or something like that, okay? So we have a certain bandwidth in a spectrum located around a certain carrier. Okay. Band limited means that the spectrum, so the power spectral density of the signal, is supposed to be contained into a given bandwidth. So ideally, we may imagine that the power spectral density of the signal is a sort of big rectangle with support, in the baseband case, minus W plus W, so the so-called unilateral bandwidth is W hertz. And then there is a white noise, which has a power spectral density which is flat over a bandwidth which is much larger than the signal bandwidth. And then when we filter at the receiver input, we have a filter that cuts away all the noise outside. Basically, we have a noise which is frequency flat over the signal bandwidth and has a power spectral density equal to n0 half. Okay, so I will explain a bit better the relation between the discrete additive wide Gaussian noise channel and this physical waveform channel, this band limited waveform channel. But let me go quickly through an informal argument that allows us to quickly obtain a formula for this continuous time band limited model. We have not talked about continuous time, and we will not talk about continuous time forever in this course, but at this point, and this is the link, for band limited signals. Continuous time for infinite band signals, so without this limitation, is quite different, and it requires much more sophisticated mathematical tools of continuous time signal process, random processes, okay? But we will not touch that. Also because, especially in applications like communication, basically every communication system in the world has a finite bandwidth or approximately finite bandwidth, so this finite bandwidth treatment is good enough. Okay. So the informal argument goes like that. So we have this band limited channel with one-sided unilateral bandwidth W hertz, and we know from Shannon sampling theorem that I will talk a little bit better tomorrow in the live session for those of you who are not familiar with basic signal processing, but I think that most of you are familiar with signal processing. We know that if we have a continuous time signal with the spectrum is contained in this interval minus WW, we can exactly represent the signal by taking samples, as long as the samples are taken at a frequency that has to be larger than 2 times the unilateral bandwidth. So we have to take samples at frequency 2W, okay? So if we sample the signal at frequency larger or equal than 2W, it is possible to perfectly interpolate the samples in a unique way and recover the signal. If we take samples at frequency that is less than twice the unilateral band, then it turns out that we have a phenomenon called aliasing, which means there are several possible waveforms that interpolate those samples. We cannot uniquely recover the waveform. So in other words, a continuous time x of t, when x of t is band limited, is like in one-to-one correspondence with its samples xi taken at, let's say, frequency at least 2W, and since we want to be as parsimonious as possible, in order to approach the capacity, we will consider to take those samples at exactly frequency 2W. If we take samples at a higher frequency, it means that we are like over-representing. Those samples become redundant, okay? And so clearly we are overusing the channel. So this of course works also in the reverse mode. So if we generate a sequence of discrete samples xi, and then we basically play back them at frequency 2W, well, we can generate essentially any arbitrary waveform which is band limited into minus WW, okay? So there is a one-to-one correspondence between the continuous time band limited waveforms and samples transmitted at rate 2W. So let's look at a few things. What is the noise power? Well, if you use a spectrum analyzer and you measure the noise power by simply, taking the power spectral density and integrating over the signal bandwidth, you're going to find the noise power N equal to simply N0W. So N0 half times 2W gives you N0W. What is the signal power? Well, the signal power is energy per symbol, or energy per sample in this case, times the rate at which the samples are transmitted, because power is energy per unit time. And the rate, I say, is 2W. So we have 2 WES, and therefore the signal to noise ratio defined in terms of physical quantities, signal power over noise power, is precisely the same quantity that we have called SNR before. It's 2ES divided by N0. So now let's see a capacity of the continuous time channel in bit per second, right? There are no symbols in continuous time. There are seconds. We want to say the bit rate is bit per second. It's megabit per second, gigabit per second. This is how you measure the rates in the real world, okay? So the capacity in bit per second is obtained as capacity in bit per symbol times the number of symbols per second. But the capacity in bit per symbol is this quantity we have already computed, and the number of symbols per second is the playback rate of our signal samples, which is 2W, and therefore we arrive, oopsie, what happened? We arrive to the famous, even more famous formula, also referred to as Shannon Formula, that the capacity of the band-limited AWGN channel is W, the channel bandwidth, times log of 1 plus SNR. And this is measured in bit per second. So for example, with this formula, you can very easily understand why your Wi-Fi system can transmit at, let's say, 50 megabit per second. You have a bandwidth of, let's say, 40 megahertz. So this W is 40 megahertz. And then you need just that this log of 1 plus SNR is 5/4 to get 50 megabit per second. Okay? So you need a little bit of SNR. And of course, a very good communication system that in fact approaches this limit. It's not easy. There's a lot of coding, a lot of very cool signal processing to approach this limit. What happens to the passband channel model? So when we have a channel located around a carrier frequency, then now the unilateral bandwidth is again W, but now we have W here and W in the negative frequencies, right? The power spectral density of the noise is always N0 half. Now what happens is that through communication theory, when we demodulate a passband signal, we can demodulate by multiplying by the carrier in phase, so by a cosine, and the carrier in phase quadrature by a sine. So we get two signals after demodulation. One is the real part, or the in-phase component, and the other one is the quadrature component, or the imaginary part. So if we represent these two components as a real and imaginary part of a complex signal, we get what is called a complex baseband equivalent channel model. And it turns out that this is basically a baseband channel where the signal is now complex as a real and imaginary part. The one-sided bandwidth now is W half, because the whole bandwidth located around the origin is W, and the power spectral density of the real and imaginary part of the noise is N0, where we have N0 half for the real part, N0 half for the noise, for the imaginary part, so, and the real and imaginary part are independent. So this is exactly a process that corresponds to what we called before as a proper Gaussian random vector, random process, and or circularly symmetric Gaussian, complex Gaussian random variable. So the noise samples have these statistics. So what happens is that here we say, this is what I just said, so the noise is a complex circularly symmetric with variance N0. The noise power, when you see from here, it is simply N0 times W. The signal power, now if we take X to be also complex Gaussian with variance ES per complex sample, now the signal power is, you see now we are, the one-sided bandwidth is W half, so twice this is W. So for the same argument as before, we have energy per complex symbol ES. We transmit a complex symbol every 1/W seconds. So in total, the power is ES times W. And so again, the signal to noise ratio in the complex channel model, which is again power of the signal divided by power of the noise, is given by ES over N0. And now it turns out that if we repeat the capacity calculation for the complex circularly symmetric Gaussian channel, we find that the capacity in terms of bit per symbol, now complex symbol, is given by this formula, where this is precisely the same thing here, okay, is ES over N0. So again, now we can calculate the capacity in bit per bit per second by taking bit per complex sample times number of complex samples per second, and we arrive at exactly the same formula as before, where simply SNR has a different definition. In the real case is ES over the noise power spectral density of the real noise, so N0 half, and in for the passband channel model is ES over N0. Okay. So, but the concept of W is the same. Before it was the unilateral bandwidth of the baseband channel, and now this W is the unilateral bandwidth of the modulated channel around the carrier. Okay, good. And notice that in both cases, ES over N0 for the complex model and 2ES over N0 for the baseband model, in both cases the SNR is always physically the signal power divided by the noise power. So this is a quantity that has a very clear physical meaning. Okay. Very good. So at this point, I make another little pause because otherwise the video becomes too long and then I cannot upload it on the system. And in the last part, we're going to talk about a generalization of this channel model, talking about parallel Gaussian channels, and in particular introduce a model for the channel with intersymbol interference, which is the model is closer to the real-life communication theory channels, and a specific capacity achieving procedure, which is like the information theoretic version of OFDM, orthogonal frequency division modulation, which is, for those of you who know, who have studied a little bit of communication theory, OFDM is the modulation of choice in systems like modern Wi-Fi, LTE, 5G, so, and in various other systems for cable transmission, like for example the fast version of DSL that allows to obtain a lot of bit per second over copper lines. So we stop here and recover in the fourth part.